There was a time when 60,000 miles meant an engine was just getting started, not worn, not fragile, just broken in. That era is over, but mostly outside the United States. In Europe, automakers have been forced into a very different engineering philosophy, one driven not by durability but by regulatory pressure, engine size penalties, CO2 targets, test cycle optimization. The result? Engines engineered to survive the warranty period, not a lifetime. Today, we're not talking about American V8s or long-stroke truck motors. We're looking at what happens when engineers are pushed into extreme downsizing. Most of these engines were never sold in the US, and after seeing what they do to owners, you'll understand why. These are 7 European engines that quietly turn cars into financial time bombs. Number 7. Fiat 0.9. Twin Air. When 2 cylinders are one too few. Europe thought this was the future. The Fiat 0.9-liter twin-air turbo-cut engine design down to the absolute minimum. 2 cylinders, 875 cubic centimeters, big turbo boost. On paper, it looked brilliant. In reality, it exposed a basic truth of physics. 2-cylinder engines shake violently. To control the vibration, Fiat added a heavy balance shaft. That only shifted the stress elsewhere. The dual-mass flywheel absorbs brutal combustion pulses and often fails before 40,000 miles. The turbocharger runs at the edge of thermal survival just to make usable power. Cracked exhaust manifolds and worn bearings are common. Then there's Fiat's multi-air valve control system, extremely sensitive to oil quality. Miss one oil change and microscopic oil passages clog. Replacement cost over $1,000 on a car often worth less than $4,000. This engine was never sold in the US, and that's no accident. Number 6. Opel 2.0 CDTI, killed by a $15 seal. This engine was strong, well-designed, respected, and it was destroyed by a cheap rubber seal. The seal sits between the oil pump and its pickup tube. Over time, it hardens and shrinks. The oil pump starts drawing air. Oil pressure builds too slowly during cold starts. Bearings run dry. By the time the warning light appears, the damage is already done. Preventive repair costs a few $100s. Ignoring it leads to complete engine failure. Opel never sold cars in the US, but this is a perfect example of how a single overlooked component can destroy an otherwise solid engine. Number 5. Mazda 2.2. Skyactiv D. When even Japan gets forced into bad design. Mazda is known for conservative, durable engineering. This engine proves what happens when regulation overrides tradition. The 2.2-liter Skyactiv D diesel, used widely in Europe, suffers from faulty camshaft surface hardening in early versions. The exhaust cam wears down. Metal particles enter the oil. Those particles destroy. Turbocharger bearings vacuum pump screens, sometimes eliminating brake assist. Crankshaft main bearings. At the same time, aggressive exhaust gas recirculation clogs the intake with soot. During diesel particulate filter regeneration, fuel washes into the oil. The oil thins. Lubrication collapses under load. This diesel was barely sold in the US, and when it was, failures were often covered by extended warranties. In Europe, many owners weren't so lucky. Number 4. Hyundai and Kia 1.6 GDI, destroyed by its own emissions. Hardware. This one sounds unbelievable until you see the engines. The 1.6-liter GDI engine uses a catalytic converter mounted extremely close to the engine for faster emissions warm-up. Over time, vibration breaks down the ceramic core. Fine ceramic dust forms. Thanks to variable valve timing, that dust is pulled back into the cylinders. Ceramic dust doesn't burn, it grinds. Cylinder walls are sandblasted. Compression collapses. Oil consumption explodes. In the United States, Hyundai and Kia were forced to replace massive numbers of engines under warranty and legal settlements. In Europe, the same failures often meant out-of-pocket engine replacement. Same engine, very different consequences. Number 3. VW 2.0 BITDI, the engine that killed vans and bank accounts. This engine destroyed more than vehicles. It destroyed livelihoods. The VW 2.0-liter bi-turbo diesel, installed in European transporter vans and pickups, used an aluminum EGR cooler. Exhaust gases corrode the cooler from the inside. Aluminum oxide particles break loose. Those particles are extremely abrasive. They enter the combustion chamber and grind piston rings and cylinder walls. Oil consumption rises beyond 2 quarts per 1,000 miles. By the time the warning signs appear, the engine block is already ruined. Replacement cost, up to $15,000 installed. This engine was never sold in the US. American emissions rules kept it out. In hindsight, that may have saved a lot of families. Number 2. Renault/Nissan 1.2 TCE and DIG-T Europe's oil-burning scandal. This engine didn't just fail, it ended up in court. The 1.2-liter turbo gasoline engine, known as TCE at Renault and DIG-T at Nissan, was installed in millions of European cars. Its flaw is simple and devastating. During deceleration, intake vacuum pulls oil past the piston rings. Weak oil scraper rings fail to remove it. Oil consumption skyrockets. 1 quart every 600 miles is normal. That oil burns and leaves carbon deposits on exhaust valves. The deposits trap heat. Valves overheat, crack, or drop pieces into the cylinder. The engine doesn't limp. It dies, often before 50,000 miles. Software updates came too late for many engines. Cylinder walls were already damaged. This engine is largely a European problem. US buyers were mostly spared, but it shows exactly how early small turbo designs failed under real-world use. Number 1. Ford 2.0 EcoBlue, when Europe exported a bad idea. At number 1 is an engine that proves efficiency on paper means nothing in the real world. The Ford 2.0 EcoBlue diesel uses a timing belt that runs inside engine oil. The idea was reduced friction and better fuel economy. The reality? Oil, especially when diluted by biodiesel during short trips, chemically attacks the belt. The belt sheds material. Debris clogs the oil pump pickup. Oil pressure collapses instantly. The engine doesn't warn you, it just dies. These engines power work vans. When one fails, it's not just a repair bill, it's lost income, lost contracts, lost time. This design is far more common in Europe than in the US, and once again, American buyers were largely protected by different standards and service expectations. European engineers didn't forget how to build engines. They were forced to prioritize regulations over durability. America took a different path. Bigger margins, lower stress, more tolerance for real-world driving. These engines are not accidents. They are the predictable result of extreme downsizing. And they explain why many American buyers never see these failures unless they import them. And here's the uncomfortable question nobody wants to ask. If engineers clearly know how to build durable engines, why are so many modern ones built with almost no margin for error? Is it really about saving the planet, or is it about passing laboratory test cycles at any cost? Because when durability becomes secondary to compliance charts, guess who pays for the experiment? Not regulators, not corporate executives, owners. Europe pushed engineering to the edge. America mostly refused to follow. The real question is, how long before that pressure spreads everywhere? If you think reliability should matter more than regulatory box checking, hit subscribe. And tell me in the comments, are modern engines over-engineered or intentionally underbuilt? Let's talk about it.